Right. Hello everyone, and today we will be discussing one-sided limits and the sandwich theorem. To jump in straight away, I would like to discuss the theory of one-sided limits. So, say for example, we have two functions here. They're quite obviously discontinuous in some certain ways, but they have, certain points here, and they're both approaching, as we can see, 1.5, x equals to 1.5 from different sides. So if we were to write out the function limit of f of x equals to, well, as x approaches to 1.5 from the left-hand side. Okay, and here we will learn about what is the left-hand side and the right-hand side of limits. And it is as follows. So if we were to be approaching, right, this point, 1.5, from all like negative values, values that are less than 1.5, my apologies. They don't necessarily have to be negative on this part. It just really is depending on this graphing point, 1.5. So if it is approaching from different sides, so for example, when x is equal to 0, when x is equal to 0.5, when x is equal to 1, and then 0.49, like really close from, as we can see from the left-hand side, how much will it be equal to? And we can see that it is all like kind of pointing towards 2, y equals to 2. So then we can just equate it to 2. Then we can look at this function, and this will be the limit of f of x. Like, how would it be looking like if we were approaching it from positive values? So the limit of f of x as x approaches 1.5 from positive values, or from the right-hand side, because as we can see, it's going to be going like this. So first we have x when it equals to 3, and it's here, and then we have x 2.5 when it equals to here, and then x2 and 2.5 quarters, and 2.6, 2.51, and it's all approaching until 3. Y equals to 3, and we can just write that out as 3. And since these two, my apologies. Sorry. And since these two don't seem to be equaling to each other, we can then say that the limit of f of x as it approaches 1.5 does not exist. And that's basically the gist of one-sided limits. Basically, we look at limits from one side, depending on the question, whether it is asking from the left-hand side, which means that it is approaching x, the given x that we need from values that are less than the value that we want itself. In this case, it's 1.5, so this can be 1.01, 1.41, and then 1.49, 1.444999, and so infinitely. And then we can look at from values that are greater than the x value that we want, and do the same procedure essentially to see how it will be. And one important rule is that if the two match, and they are supposed to match, then we know that the limit is existing and continuous. So for example, like if we were looking as x approaches to 3, we can see that as x approaches to 3 from the left-hand side, or from values that are less than 3, so for example, x equals to 2, it then equals to somewhere around here, like 3 point something, and then 2.5, that's going to be equal to 3.5 if I'm not mistaken, and then eventually it's going to approach to 3, and it's going to be 3.5 on the dot. Let's just denote that, 3.5. And then if we're looking at it from the right hand side, then values that are greater, then we can see that it's 4, then it's going to be 3, and then it's going to be 3.5, and it's going to be somewhere around in that region, like 3.4 something. And it's also approaching that same dot. So they are equally approaching y equals to 3.5. So therefore, the function will indeed be continuous. But that is one-sided limits. Now let's move on to the sandwich theorem. And for the sandwich theorem, let's just suppose 3 instances with food. Let's say we have pasta, because I really like pasta and I ate some yesterday. And then we have a pomodoro morta, or like eggs, fried eggs, scrambled eggs, and a bowl of noodles or something like that. And say, for example, we know, this isn't factually accurate, please don't fact check me on this, but that there are as many nutrients in some pasta as there is in eggs. And so we're just going to write that out. We're going to say that pasta has as many, the function of pasta has as many nutrients as this bowl of eggs. So eggs, you know, or less than, you know, something close by. These are the eggs. And then we also know that the eggs have as much, if not less, nutrients. Well, let's just denote that as n then, if it's in terms of nutrients, as this bowl of noodles. And then we just add that here and we say noodles n. So we know that these are all relevant of each other. So if on a given day, for example, the pasta will have 15%, well, that's not a number, let's just make it like, I don't know, 150 nutrients, and then we know that the bowl of noodles is also 150 nutrients, then it must like unequivocally mean that the eggs will also have 150 nutrients. That's just kind of a rule of thumb. So henceforth, we can denote that if we were, for example, to have some sort of function, and there would be, the function would be something like this, and this would equal to f of x, and then we would have another function that would be like so. And let's denote this as 1, and, you know, and then we have some, and this will be g of x, and then we will have some other function which will be like right there in the middle. And here you can kind of see why it means sandwich, because it's sandwiched between these two functions, and let this be h of x. We can, from this thing, evaluate that because, say, the limit of this function is here, right? That the limit of f of x is equal to L, and that the limit of h of x is also equal to L. And then we will completely know that the limit of h of x will also be between these two, so it will also equal to n. So the limit of these two functions will be the limit of the middle function that we tried to find. And that is the sandwich theorem.